Okay, so we want to make a definition here. So when we say limit cycle, we're going to talk about a closed orbit that is isolated. So examples of what this might mean. Maybe we have, this is our closed orbit, and inside we might have a spiral that's coming out towards it. On the outside, we might have a spiral that's coming down. And so this would be a stable limit cycle, because any orbit that starts near it gets closer to it, both on the inside and on the outside. So the limit cycle itself is this closed orbit with the blue arrows, right? And inside of it, there's a spiral that is an unstable spiral, but it's in the future, it's going towards the limit cycle. And on the outside, things are spiraling down towards the limit cycle. So that makes it a stable limit cycle. We could also have, if this is blue thing is our limit cycle, if things spiral away from it, we could have an unstable limit cycle. So in this case, we again have an isolated orbit, but our isolated orbit trajectories near that aren't on the isolated orbit are running away from the isolated orbit. And then of course you could have something that's sort of half stable. Right, so if we have some isolated orbit here, and it can be half stable in a couple of different ways, right? It could be half stable in two different ways, right? So maybe on the inside, we're spiraling out towards it, but on the outside, we're spiraling away. So now this half stable limit cycle is a stable, on the inside, trajectories are coming out towards it, but on the outside, trajectories are swinging away from it, right? And then, so that compares to, say, the unstable limit cycle, in which the trajectories that start close to it go away from it, both inside and outside, and the stable limit cycle, where trajectories both inside and outside the limit cycle are going towards it. That sort of makes sense? People good?
Yep, all good here.
Okay. Yep. Now, centers, simple harmonic oscillators, periodic orbits. So if you have something that looks like this, these are not limit cycles. Why are they not limit cycles? The orbits are closed. What in the definition makes it not a limit cycle?
It's not isolated because
Yeah, they're not
there's
isolated,
multiple.
right? The closed orbit is not isolated. So in order to be because it's not, so the closed orbits are arbitrarily close to other closed orbits. Right, so to be a limit cycle, it has to be isolated. Okay, good.
Good.
So for example, if I work in r theta coordinates, I could do r dot is r times 1 minus r squared, and theta dot is 1. So theta dot is 1 means I'm going to go counterclockwise at a constant rate. But here, I see that if r is 0 or r is 1, we're going to do this. R is the radius, right? So it has to be greater than or equal to 0. At r equals 0 and r equals 1, I have fixed points. So if I plot r dot versus r, this looks like that. So here's 1. And we see that there's a stable fixed point in the r dot plane at r equals 1 and an unstable fixed point at the origin. So this, if I looked at x, y, where x is r cosine theta and y is r sine theta, then what I would have is a circle at r equals 1. And then I would have an unstable spiral coming out. And on the outside, it would spiral down onto it. That sort of makes sense. So that my circle at r equals 1 is my isolated limit cycle. Inside, there's an unstable spiral, and outside it's spiraling down like it's a stable spiral, but it gets stuck at r equals 1, right? So a stable spiral would keep going all the way down to the origin. But if I have a stable limit cycle, then that stable spiral outside of the stable limit cycle just sort of collapses down to the circle. That good? Okay. Okay, so this next one is a historically important one. Called the van der Pol oscillator. So in the van der Pol oscillator, we have x double dot plus mu times x squared minus 1 times x dot plus x is equal to 0, where mu is some positive number. So this is, if I look at it, right, this is like an RLC circuit. So in an RLC circuit, you have a second order differential equation. You can have various modes that happen, but it's a nonlinear version of something like that, right? So this term in here adds some nonlinearity to the system. And so if I look at what I've got here, when x is more than 1, then the term in front of x dot is positive, which means that, let's remember, like if I had x double dot plus 3x dot plus 4x is equal to 0, we would call this a damped oscillator. And it's, of course, a linear system. And it's going to be a stable spiral, right? So a simple damped oscillator would be a stable spiral. And the way that we know it's a damped oscillator is that the term in front of the x dot is positive. So when x is more than 1, x squared minus 1 is positive. And so in that case, we have damping. But if I go back to x double dot plus mu times x squared minus 1, x dot plus x is equal to 0. But if I look at x less than 1, x squared minus 1 is less than 0, which means that the term out front here is negative. Which means that the spiral that we have at the origin is unstable. Good.
Yep.
And so if you plot, you can make some plots. This is a nice one to do in MATLAB or Python or something. There's a sort of a funky looking oscillator here. So there's a closed isolated orbit here. And on the inside, you spiral out to it. And on the outside, you spiral down to it. And if you plot x versus t, it has some sort of weird oscillator. Not a nice smooth sine graph. It's some sort of weird oscillator. Okay. So the Van der Pol oscillator is a historically interesting one, and it's worth, some point in your life, it's worth dropping it down into some Python code and just seeing what it does, right? So turn it into first order differential equations and solve it with your system. Okay, good. Daniel, yes?
Yeah, I'm good.
Okay, now, people spend lots of time trying to prove that their given system does not have any periodic orbits, right? So one thing you want to do is try to show that you do or do not have periodic orbits in a given system of equations, right? So here's a couple of examples of ways that you can rule out periodic orbits, and then we'll write down a theorem for how you can prove that there is a periodic orbit. So one of the ways you can write down for ruling out periodic orbits is something called the Lyapunov function. And, I think the main reason we're going to talk about this one is I like saying the word. Everybody say Lyapunov.
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 No.
Is that one of the Russian physicists?
Yeah, it's a Russian word.
Okay.
So the key to pronouncing Russian words like a Russian as opposed to like an American is that you have to put the emphasis on the second syllable, not the first. Right? So you got to put the emphasis on the p, not the li. Okay? So it's never the first. So Russian looking words, you want to sound like you know what you're talking about, and you run into a Russian looking word, you put the emphasis on the second syllable, not the first syllable. Okay. So a Lyapunov function is an energy-like function that decreases along all trajectories. So the motivation here is, let's suppose that we have a damped oscillator. So in a damped oscillator, every trajectory ends up at the origin. But from a physics standpoint, there exists an energy, 1/2 mx dot squared plus 1/2 k x squared, right? So there's this function, the energy, and E is everywhere positive, right? So 1/2 mx dot squared plus 1/2 k x squared, that's everywhere it's positive, but E dot is negative because I'm spiraling into the origin, right? I'm losing energy in the damped oscillator, right? So if I have a damped oscillator, then I can construct this function called the energy, and the energy will be positive everywhere. If it was a simple harmonic oscillator, E dot would not be negative, right? But E dot is negative everywhere in the phase plane on every trajectory. And so because that's the case, you end up spiraling into the origin. You end up losing all of your energy. Okay. So the principles of the Lyapunov function, the idea of the Lyapunov function is that we're going to say let x vector dot be equal to f of x vector. It's a 2D system with a fixed point of x star. And then we say the following. Suppose we can construct a function v of x, and it's going to be real valued. It's going to be continuously differentiable. V of x is greater than 0 for all x not equal to the fixed point, and v at the fixed point is equal to 0, and v dot at x is negative for all x not equal to the fixed point value. Then you can show the theorem is that x star is globally asymptotically stable. Okay, so remember, a fixed point is asymptotically stable if trajectories near it approach it in all directions. So if all trajectories near a fixed point approach the fixed point, it's called asymptotically stable. If the fixed point is globally asymptotically stable, you're basically saying that everywhere in space, you end up going to the fixed point. So the idea is if you can find this function v of x such that it's 0 at the fixed point, it's positive everywhere else, and its derivative is negative, then you know that the fixed point that you found is globally asymptotically stable and there are not any periodic orbits. Okay, so let me try to do an example. So let's suppose that we have x dot is minus x plus 4y. And y dot is minus y minus, or minus x minus y cubed. Okay, so it's non-linear at this spot. Okay, obviously x, y is 0, 0 is a fixed point. So the origin is a fixed point. All right, if I stick in both x equals 0 and y equals 0, I have both x dot is 0 and y dot is 0, so that's a fixed point. Good? So I'm just going to write down a guess. X squared plus AY squared, where A is some number. So I'm just giving myself a little flexibility, and A is going to be some positive number. So now V dot would be 2x x dot plus 2ay y dot, right? So if I take the time derivative of the function v, I would take the derivative with respect to x and then multiply by x dot, and then take the derivative with respect to y multiplied by y dot. But I know that x dot and y dot are up here. So v dot is 2x times minus x plus 4y. And then I'm going to add 2ay times minus x minus y cubed. And so if I clean that up a little bit, I get minus 2x squared plus 8 minus 2a times xy minus 2ay to the fourth, right? If I just multiply everything out. And then a was free, right? So my goal is just to find any function v that has the properties that it's 0 at the origin and positive everywhere else, but I want its derivative to be negative everywhere. So let me pick a equals 4. If I pick a is equal to 4, then that wipes out this center term. And v dot is minus 2x squared minus 2. Well, if I picked a equals 4, then the a becomes, this becomes an 8 y to the fourth. And I see that I have satisfied the conditions, right? So I found a Lyapunov function. It's this, my Lyapunov function is positive everywhere except at the origin, which was the fixed point where it's 0, and its derivative is negative everywhere. So that means that the origin, I've ruled out the fact that there could be any limit cycles. Sound good?
Yep.
Yes.
Okay. So there's a couple of other ways to prove there's no fixed points. I'm going to skip them. You can read about them in the book if you ever buy the book. And I want to tell you about the Poincaré-Bendixson theorem, because it introduces some neat ideas in mathematics too, right? So the idea of a Lyapunov function is a useful idea in math, right? The idea is you want to make sure that you can prove that everything is flowing downhill, basically. So by constructing this function, which is whose derivative is negative along the flow, that basically tells you that you're always decreasing in like some energy-like function. Okay, so now the Poincare-Bendixson theorem introduces the idea of trapping regions, which is a useful thing to do in mathematics as well. So this is a theorem proving the existence of a limit cycle. The basic picture of the Poincare-Bendixson theorem is that you make some disc-shaped region, right? So I'm going to be interested in the region in here. Can you see my yellow?
Yes.
Okay. So now this region I'm going to call R. Okay. Now what I'm going to say what I want to have happen is I want to pick my region R such that on the outer boundary, the flow is into R. But then on the inner boundary, the same thing is true. Now, if the flow is into R on both the inner boundary and the outer boundary, there's only two possibilities. One possibility is that there's a fixed point somewhere in there, right? Maybe somehow the flow is going into this region because it's going to spiral around and stop at some place. Or there could be a limit cycle. So if I have the flow falling into these regions, what we say is that R is called a trapping region. So the idea of a trapping region is a really useful idea in mathematical proofs. So what I've said here is that the flow is into this region and can't escape from it. So I have a trapping region. If I can show that I can create a trapping region and there are no fixed points in R, then R must contain a closed, isolated trajectory. And you can write out the words in more formally mathematical language, right? But the idea is if you can find a subset of the phase plane where the flow goes into it from all of the sides, then you created a trapping region because the flow can't get out of it. And once the flow has to gets into it, there's really only two possibilities. One possibility is that there's a fixed point somewhere in there, one or more fixed points, in which case you end up at the fixed point. But if you can rule out that there are no fixed points, then once you've established a trapping region, then you know that there has to be a a limit cycle inside. Good?
Good. So we're going to have positive derivatives because of that, right?
Yeah, so in the instance that there is a limit cycle, then you wouldn't be able to create one of these Lyapunov functions. Right, so you'll see that creating a Lyapunov function sometimes is easy and sometimes is brutally hard. Right, you know, it depends on what your dynamical system looks like. If your dynamical system is simple enough, then you can kind of guess around. There's a couple of initial guesses, like this Lyapunov function here kind of looks like a potential energy term. Right, so you try stuff like that. It's going to be positive everywhere. So for both x and y, positive or negative, v is going to be positive. It's 0 at the origin where the fixed point's supposed to be, right? But if you try a couple of these and you can't, and they don't work, then you haven't proven whether there's a limit cycle or not, right? So if you can construct a Lyapunov function, then you know there's not a limit cycle. But whether or not you can construct a Lyapunov function is guessing about functions and seeing which one might work, right? You literally just guess until you find one. There's no great way of knowing what Lyapunov function should be, right? On the other hand, if you can create a trapping region and there's no fixed points in the trapping region, then you know that there is a limit cycle. You haven't found the limit cycle. You don't know exactly what its shape would be. You could try to squeeze the region and make the region smaller, and so you could limit the shape, but you haven't figured out what the shape is, but you know there is a limit cycle. All right, and so whether or not one of these things is easy or not is sort of not particularly obvious. All right, this sort of makes sense?
Yeah, I'm following.
Okay. All right, so all right, so when we did one-dimensional flows, we had bifurcations. That's when the fixed points changed in their character. Okay, so 2D bifurcations come in two varieties. We can create or destroy fixed points. We can create or destroy limit cycles. And then, yeah, okay, so we'll go with that. Okay, so these are the types of things that we can do, right? So in two-dimensional flows, we still have fixed points, but the fixed points are surrounded by saddles or nodes or things like that. And then we have limit cycles, which are these isolated closed orbits. And those are the interesting structures. Okay, so creating and destroying fixed points. The easiest way to create or destroy fixed points is in the saddle node bifurcation. So this is the thing that we called the blue sky bifurcation in the last, when we did it in one dimension, and sometimes we called it a saddle node bifurcation. And we now know about saddles and we now know about nodes. And the idea is that the reason you call it a saddle node bifurcation is that your two-dimensional system has a saddle and a node that crash into each other. So if we have x dot is mu minus x squared and y dot is minus y, then for mu positive, there's a saddle here at the origin and a stable node over here at mu. So for mu negative, oh, sorry, mu positive. We have a saddle next to a node. Okay, good. And so this position over here, this is at x equals mu. All right, if I look at this here, I see that x equals mu, or square root of mu, I guess it is. X is the square root of mu, is the location of this node. So if I take mu and I let mu go to 0, the node moves towards the origin. And so at mu equals 0, the saddle and node combine. Okay. And then if mu is negative, then the flow just becomes oh no, wait. This is not. Yeah. This is okay. You end up with a bottleneck near the origin. This is something we didn't, I think we kind of skipped over the concept of bottlenecks, but I don't want to come back to them real quick. So let's suppose let's go back to 1D flows. So let's do x dot is alpha plus x squared. And let's let alpha be positive and small. Okay. So if x dot is alpha x squared, I have a parabola. Good. Everybody good? And remember, this is a 1D flow. So I'm just going to move along the right. Yes. But over here, I'm going to go fast. And over here, I'm going to go fast, right? Because I've met large x dot, right? Fast. So I'm moving fast there, but I'm moving very slowly here. And so this region in here is called a bottleneck. You know, like when you're driving a car and you got a bunch of merging that goes on, right? You have a bottleneck in the flow of the traffic, right? You got a region where you have to go very, very slow through it, and then it speeds up as you come around. And the bottleneck has shown up because I've undergone a saddle node transformation, right? So bottlenecks are symptoms of a saddle node. bifurcation. Right, so if I have a saddle node bifurcation, where I take this and I make alpha go negative. Once alpha goes negative, I have a stable and an unstable fixed point. Yes, good. Okay. So when the saddle node bifurcation happens, which is alpha equals 0, I stop having a stable and unstable fixed point. I end up with this one metastable fixed point. But then if alpha is tiny but positive, the flow looks like it's getting stuck at the origin still. So this bottleneck idea shows up because of the saddle node bifurcation. And so in 2D flows, what happens is you'll have a region where you have the ghost of the former fixed points. So even when mu is 0 and there aren't any fixed points around, if you tried to watch the system, it looks like it's running towards the origin and stopping, but eventually it pulls through and then speeds back up. So again, you'll be going kind of fast along the trajectory out here, and you might be moving fast along the trajectory here again, but you're going to move really slow in the region near this bottleneck, the ghost region. Okay, good.
Good.
Okay, so you can also have so you remember our 1D, we had the transcritical, I can't spell. Oh, crap, that's awful. Bifurcation, which had the form x dot was mu x minus x squared. Or we had the pitchforks, where we had x dot is mu x minus x cubed, or x dot is mu x plus x cubed, right? So in 1D, you have just that much. If you stick on y dot is minus y, you can come up with all of these other types of bifurcations. Okay, so just by taking your 1D bifurcation and sticking on y coming basically down. So y dot is minus y, just makes y want to go vertically downwards. Good?
Yep, good with that.
Okay. So, for instance, if I have, what I want to do, if I have x dot is mu x minus x cubed and y dot is minus y, which is the super critical pitchfork. Okay. Then you can draw out what you get for mu negative. The only fixed point is the origin. For mu equals 0, that's still true. But what happens is these arms get very flat this way. And then for mu positive, the origin becomes a saddle. and you pick up stable nodes on the sides. So if I look at what's happening on just the x-axis, I have a stable fixed point, and then it becomes two stable fixed points, and then the origin becomes an unstable fixed point. So I look at just the x-axis, I have the supercritical pitchfork. But because I'm also now moving vertically down, those stable fixed points on the x-axis become parts of nodes or saddles. And the unstable one becomes part of a saddle. That sort of makes sense?
Yeah, I follow that.
Okay, so this is not super interesting. All right, the thing that's much more interesting is called the hop bifurcation. Okay, so these are all, so all of your 1D bifurcations, the saddle node, the pitchfork, the transcritical, have 2D components. Okay, now the limit cycle that's a new 2D feature. And so, but we have something called the hop bifurcation. So if I do the following, I do r dot is mu r minus r cubed, and theta dot is omega plus b r squared. And we're going to vary mu. What you'll see is that for a mu negative, what you have is a stable spiral. So at mu negative, you have a stable spiral. Because if I look at this R equation, right, and I solve R dot is equal to 0, what I would have is R times mu minus R squared needs to be equal to 0. So that the solutions are R equals 0 and R equals plus root mu. So if mu is negative, the second one here is not a real root. So the only R value that's not changing is the origin. Okay, but if mu is positive, then there's an R value. So this radius here is plus root mu, is that radius. There's a particular R value that doesn't change in the flow. And the origin is still doesn't change in the flow. But what's happened is this thing is going around. And I drew my thing badly. I drew my spiral badly. I need to draw my spiral coming around this way. Because this is going around that way. And what's happened is outside comes down, but it gets stuck on the limit cycle at root mu. And on the inside, it flips around to being an unstable spiral. So this is a stable limit cycle here. So the idea is that the origin switches from the fixed point at the origin at mu negative is such that that fixed point is a stable spiral. The stable spiral at the origin changes character at mu equals 0 and becomes an unstable spiral. And once it becomes an unstable spiral, a limit cycle is born outside of it that's a stable limit cycle. So if you are at large, if you start off, somewhere out here at P, in either one of these cases, you start coming towards the origin. For mu negative, you spiral all the way down to the origin. For mu positive, you spiral down towards the origin, but then you get stuck on the limit cycle. And inside the limit cycle, things are spiraling out towards it. So this is a bifurcation that happens at the origin. But then as the parameter grows, you grow a sizable limit cycle. So the limit cycle grows out from the origin. Right? So there's no limit cycle at all. And then a little tiny one forms at the origin and expands out. So this is the birth of a limit cycle at the origin. And this particular one is called the supercritical Hopf bifurcation. There's also a subcritical Hopf bifurcation where you do the other thing, where you had a, so this particular one here, this is of the supercritical type. You can do a subcritical Hopf bifurcation. And the best way to think of that is that you had a stable limit cycle. So how do I want to think of this? Let me draw it the other way. I have a stable limit cycle out here. And inside there is a, no, This isn't the right way to think of it. So what I want is I want the limit cycle to be unstable. So this is actually kind of a cool thing right here. So this is an unstable limit cycle. So that means that trajectories that start near it spiral down to the origin, and trajectories that start near it on the outside spiral away. Okay, so an unstable limit cycle is separating two regions. One region is spiraling away to infinity. The other region is spiraling down to the origin. And the idea is that you shrink your unstable limit cycle away until you get an unstable spiral. So the idea of the subcritical Hopf bifurcation is you start with an unstable limit cycle that shrinks to the origin, and when it reaches the origin in size, it turns over into being just an unstable spiral. So whatever's happening outside of the limit cycle, that behavior has to go all the way down to the origin. So in the unstable limit cycle, what's going on outside the limit cycle is it's running away to infinity. So if you shrink the size of that limit cycle, eventually it becomes an unstable spiral. Okay. So you go from having a stable spiral. So this blue curve, the spiral inside of the limit cycle is a stable spiral. It's spiraling down to the origin. The stable spiral disappears and the whole thing becomes an unstable spiral.
That makes sense.
All right, so these are bifurcations that all take place at one point. So the key thing to understand here is that our 2D analogies of the 1D bifurcations plus the Hopf bifurcations all take place at one point, right? So the bifurcation action happens when two, like in the pitchfork, the one stable splits and becomes two stable and one unstable. So the place where the splitting happened at one point, or the limit cycle shrank to the origin. And so at the origins where the one action happened, right? So these bifurcations all happen at one point. So what we'll do next week is we'll talk about bifurcations, which are called global bifurcations, where the whole phase space changes at once globally all over the place, not happening just at one point. So there's also things called global bifurcations. And that's now very different from what happens in 1D. So in 1D, we had saddle nodes, transcriticals, and pitchfork bifurcations. Those all happen at one point, and those happen in 2D as well. Now, in 2 dimensions, we have limit cycles, which we didn't have in 1D because we have 1D, we couldn't go around, right? Couldn't cycle in 1D. So we have the Hopf bifurcation, which again, though, happens at one point. And then the idea, and this is lecture 15, if you're following the notes, is that there's bifurcations that happen to the whole plane at once. And that's what we'll do next.
That's kind of getting into fractals, correct?
It starts to, you have to get to more than 2 dimensions to end up in fractal land for maps. But we're going to get there soon.
Very cool.
Okay. Everybody good? I'm going to stop recording.